today's notes, we're going to cover section 6.4, the first day of it, which is going to cover exponential growth and decay. Now, as a background information, we know that when we're dealing with linear functions, there's multiple ways, and we learned three in our course, three different ways that we could write a linear function. We have our general form. So the most general form of a linear function is our sloped-intercept form. And the reason that we call it the most general form is because it tells us the two important things that we need to know about a linear relationship. And those two important things are the starting value, which we know is our y-intercept. So I'm just going to label that as the starting point. And then we know that the main characteristic of a linear relationship is that constant change. So again, those are the two things that define a linear relationship. So that's why in the most general form, we see those two things. Now, what we also know, though, is that there's other ways to write a line. Now, we have other forms because other forms give us different pieces of information. So, for example, this one here, this is point-slope form. So it's still a line, so we know it still has a constant change, and that constant change is still given to us. But in this case, rather than knowing the starting point, we just know a different point. We know this point x1, y1 is on the graph. So not the starting point, but just a different point. So we have different information from that other form. If we look at this form, which we know as standard form, standard form actually doesn't tell us the slope by looking at it, but what this is good for, as we've learned before, that this is really good at things like the intercepts. It's also good for like real life problems. So we have different forms of a line. So it starts with that general one, and from that general one, we could break it down into other forms that tell us other information. Now the same thing will happen with our exponential functions. We have a general form, and again, we call this the general form because it tells us the two things that we need to know for an exponential relationship. It tells us that constant multiplier, right? That was one of the most important things. And then it also tells us that starting value. So again, we call this the general form because it tells us the two most important things for an exponential relationship. Now, just like with a linear relationship, though, there's two other forms that we're going to learn today. And those two other forms are called exponential growth and exponential decay. So we can think about that just like we did up here. We have one form of a line that we could be more specific about by breaking it into other forms of a line. Same thing with our exponential. So we're going to cover two different things today, exponential growth and exponential decay. And the difference between the two, what I have up here, is we know that the b value, or that constant multiplier, is going to determine whether or not we're growing or decaying. So with exponential growth, just to be clear, our b value is greater than 1. So what we're going to say, though, what we're noticing is when we rewrite this in a different form, all we are doing is rewriting the b term. So instead of b, we're rewriting it as a different form because we can see that this a value is still in both of the equations. So if we have exponential growth, there's a few vocabulary words that we need to know in the form. So first of all, a is still that starting amount. We know that from the general form. Now, I already have this word growth factor filled in for you. Growth factor is the entire value of b. Now, we rewrite b in a certain way as 1 plus r. That letter r stands for the rate of growth. And when we write these equations, it has to be a decimal. And then t usually stands for time in a lot of these situations. It could be x. Doesn't matter what variable we use. Just like, what does that all mean? The first thing is just being able to rewrite something. So if we're writing something in exponential growth form, like we know this is growth because our b value is 1.50. So b, if that's 1.50, that's greater than 1, so we know we're doing growth. So what we have to do when we rewrite it, so the a value is still the same a value. So in our case, y would equal 3. But instead of calling it 1.50, it has to be written as 1 plus r. So we know b is the same thing as 1 plus r, and I know b is 1.50. So if 1.50 was equal to 1 plus r, I can see by subtracting 1 that r was 0.5. So instead of 1.50, I would call this 1 plus 0.50 to the power of x. So we look at the next one. Again, we can see that this b value is greater than 1. So when we write it as exponential growth, we have to write it as 1 plus something. So in this case, I would want to add 0.06. Now finally here, when I think about 2, and here we might need to show some side work, we know that b is equal to 2, but we also know that b is supposed to be rewritten as 1 plus r. So if 2 is the same thing as 1 plus r, by solving, we get 1 is equal to r. So I'd rewrite this as y equals 5 times 1 plus 1.0 to the power of x. So it's just getting us to see that exponential growth is just rewriting b in a special way as 1 plus a number. So like we have a certain common skill, like if I looked at this table, I need to write the equation for it. So like here I can see that my x's are increasing by 1. And it looks like I do have the y-intercept. So what I notice when I increase my x by 1, it looks like the outputs are just multiplying by 2. So I could write this as y equals 4 times 2 to the power of x. But if I had to write it not only in the general form, but also in the exponential growth form, that's where instead of calling b 2, we'd have to write that as 1 plus a number. And 1 plus what would equal 2? Well, that would be 1 plus 1. So that's exponential growth. So exponential growth is when our b value is bigger than 1. So exponential decay is when our b value is less than 1. But we also make sure that our b value is bigger than 0 because we're only multiplying by a number that's bigger than 0. So the same thing here, we have some vocabulary words. Like the a value is still that starting amount. The decay factor in this case is the entire b, so since it's not growth, it's called decay. But that decay factor is 1 minus r, the entire thing. Just the value of r, that's called the rate of decay. And again, that's as a decimal. And in a lot of situations, t will stand for time, or it could be x. So the thing here is when we rewrite these, instead of a decimal, we want to represent it as 1 minus a number. So for this one, we know the starting value is the same, but instead of 0.90, I could call that 1 minus 0.10. Now with something like this, if we wanted to rewrite it as like 0.75, what I'm trying to do is rewrite this. I know that b is equal to 0.75, but b in decay is 1 minus r. So if I know that 0.75 was equal to 1 minus r, if I subtract 1, and then divide by a negative, I can see that the value of r would be 0.25. So if you can't do it in your head, you can do a little math. So this would be 1 minus 0.25. So again, we're seeing that these are equivalent, right? 1 minus 0.10 is 0.90. Same thing down here, 1 minus 0.25 is 0.75. So when you see a table, we need to be able to write the equation in 2 different ways. So like here, again, I can notice that my changes in x are going up by 1. And I do notice that I have the y-intercept. And I can see this pattern in my outputs or my y values is that they're always being multiplied by a half. So in general form, I know that I'm starting at -1 and I'm repeatedly multiplying by 1/2. So if I had to write that in exponential decay, I know my b value is 1/2, which I'm going to write as 0.5. But I know in exponential decay, I have to rewrite the b value as 1 minus r. So if I know b is 0.5, by subtracting 1 and then dividing by the negative, I know that my r value is 0.5. So I could write this as y equals -1 and then 1 minus 0.5 to the power of x. So again, that's just the nuts and bolts of knowing what the form is. So you need to memorize the forms, a, and then in parentheses 1 plus r to the t, or for decay, a, and then in parentheses 1 minus r to the t. You need to know what they are and how to rewrite them. But the reason that we do rewrite them is because it helps us interpret them. So just to preface, what we're going to be working towards is working towards examples that involve things like with percentages. Like just read example number 3. We have 80,000 people that attend a festival and the attendance increases by 6%. Or in this one, my car starts at 15,000 and it loses 10%. So those are very common applications. So before we get that though, just some background information about working with percents. We know that percent means out of 100. So if you're given a percent, like 17%, to convert that to a decimal, you take the number and divide it by 100. And as it does say in number 2, to go backwards, like if I had something like 0.06, to convert it to a percent, we multiply by 100. So just the background information. So what we're working with here, the way that we want to interpret and then rewrite. So here we can see that we're given general form. One way that I want you to start to interpret general form to help us translate to growth or decay function is what I have written over here. When you see general form, you can interpret it as starting with A and keeping B% every single time. So if I look at this one, I see my A value is 4 and my B value is 1.09. So if I converted that to a percent, if I multiplied by 100, that's 109%. So I'm interpreting this as I'm starting at 4 and keeping 109% each time. So why do I care about that? Well, if I'm keeping more than 100% of what I started with, I have to be growing. So once I know it's growth, it'll help me rewrite the equation. So I know that growth is in the form of y equals a times 1 plus r to the power of t. We know a is always the a value. But when I think about my growth rate, if I had 100% and then I kept 9 more percent, right? That's 109%. It helps me better see, converting those back to decimals, this is 1 plus 0.09 to the power of t. So once I have it there, then I can do all these other things that it asked me to. They either want to identify the growth or decay rate and the growth or decay factor. So those just help us with our language. So the growth rate, that's R. So our growth rate is 0.009 or 9% growth. So then our growth factor, that's just a fancy word for B. The growth factor was 1.09. Let's try that again with something like letter B. So when I see this, I'm interpreting it as starting at 2 and keeping this as a percent. So 0.92, if I multiply that by 100, is 92%. So if I started at 2 and only kept 92% of that, I must be losing stuff, or in other words, I must be decaying. So I know I'd be using this form. So I know my A value is 2. And first I'm going to write it as percentages. I start with 100%, but then I'm losing what percent to give me 92? Well, I must be losing 8% if I'm only keeping 92%. So then I can convert those to decimals, and now I have it in decay. So 0.8, so my decay my decay rate is the R value. That's 0.08. Or in other words, we're decaying by 8%. The decay factor, that's just another word for B, so the decay factor is 0.92. We'll try this one here. Looks like I'm starting at 24, and I'm keeping 88% each time. So if I started with 100, and I'm only keeping 88%, I must be decaying. So I know it's y equals 24. So if I started with 100%, what percent did I take away to only keep 88? Well, I must have took away 12%. So then I can rewrite this as decimals as 1 minus 0.12. So I can easily see that this is my decay rate is 12%, and then the decay factor is 0.88, because that's 1 minus 0.02. The last one I wanted to address here is sometimes they look weird, so you might need to rewrite it. Here it's written in function notation. If there is no a value, so here I can see that 1.2 is getting the power of t, that means that a value must have been 1. So here I can see that I'm starting at 1, and keeping 120% each time, because 1.2, if I multiply by 100, is 120%. So I know that I'm growing. So I'm going to start at 1. If I had 100% to begin with, I must have added 20% to keep 120%. So then I can turn those into decimals. So then I can see my growth rate is 20%, because 0.20 is a decimal. Turn that into a percentage. So my growth factor, remember the growth factor is the entire b term, and I know b is the same thing as what's inside the parentheses. So that's 1.20. So the reason we talk about that, though, is because that helps us with our examples, and this is how we'll apply this knowledge. So let's work on example 3 first. So the initial attendance of an art festival is 80,000 people, and each year we increase by 6%. So I want to think of it as I'm starting with 80,000. Now, if I had 100% to begin with, I'm adding 6% more. So I know this is going to be growth. So I'd start at 80,000. I always have 100% of what I started with. Now, in this case, since I'm increasing, I'm going to add 6% to that for every year. So I just need to convert these to decimals. So now I have my exponential growth format. So once I'm here, and I can use that equation to do a bunch of stuff. If t equals 0 represents the first year, how many people will attend on the 5th year? So the 5th year, so if the first year is t equals 0, means the second year would be t equals 1. So by the 5th year, that means t is equal to 4. So here I just plug it into my calculator. So I'd write my equation. And then here you'd use your calculator to evaluate. So I'm typing in exactly what I see into my calculator and hitting enter, and I get this number. Now that's in people, so I might round that to the nearest person. So that's an example. Let's do example number 4. A website has 500,000 members, and the number of members increased by 15%. So we need to write an exponential growth function. We know it's growth because we're increasing. Now it says that we're measuring t as years after 2010. So that 2010 is the initial year, which means that 500,000 is our initial value. So we're starting with 500,000 people. Every year we're keeping 100% of who we had, but we're gaining 15% more. So we just have to convert that to decimals. So then with something like this, how many members will there be in 2016? Well, we know that t would be equal to 6 then. So we'd go to our calculator and we just use our equation to evaluate what we wrote here. So 500,000 times 1 plus. So we get something like 1,156. And right now I'm just not going to worry about the rounding. So let's do just one more example, or 2 more examples actually with our decay. So the value of a car is $15,000 and it loses 10%, which is why we're going to do a decay. So if I lose 10%, in other words, I'm thinking about I'm only keeping 90%, right? So I could write this as y equals, it starts as $15,000. Now every year it's worth 100% of what it started as, but I lose 10%. So this is y equals 1 minus 0.10 to the power of t. So use the equation to estimate the value after 5 years. Again, we would simply just plug that into our equation and use our calculator to evaluate. So I'm going to skip that in the video. In example number 8, an investment starts at $10,500 and it has 15% loss each year. So for our equation, we'd start with that much money. So we'd start with 100% of that every year, but we would lose 15% every year. So as decimals, looks like I have an extra 0 here, sorry. As decimals then, 1 minus 0.15 to the power of t. So here we want to find the value after 6 months and after 6 years. So here's just a little tricky one. We know that t is measuring years. So 6 months, we need to convert that to years. So 6 months is half of a year. So in our equation, and again, this is why we'd use our calculator, but we would get, looks like this much. Since that's money, I'm just going to round to the second. So if we had 6 years, again, we would just use our equation. And when you do it that way, just finishing that example, you get this much money.